Okay, let's unpack this. You've seen the incredible images being generated lately.
Oh, absolutely.
The detail, the creativity. I mean, I've spent way too much time just scrolling through galleries of what these models can do lately.
Oh.
It's wild, truly mind-blowing.
It really is.
Most of that is powered by these amazing diffusion models. But the big question is, and one I'm always thinking about, how do we push this even further? Make them better, more efficient, maybe even unlock new levels of potential?
Exactly. While the results we're seeing are increasingly impressive, the field is still wide open for innovation. Researchers are constantly looking for ways to refine not just the output, but, the underlying training processes and architectural approaches.
And that's exactly what this deep dive is all about. We're taking a look at a specific research paper you shared with us that proposes a brand new technique they call dispersive loss. Sounds intriguing just from the name.
It does. Our mission here is to really peel back the layers on this paper. We want to understand what this new regularization technique is, why it matters specifically for generative models, and figure out what makes it stand out from what's come before.
Okay, so let's set the stage a little. We know diffusion models are fantastic at creating images. Their magic often comes from learning to reverse a process of adding noise. Essentially, they're brilliant denoisers that can conjure images from static.
Right. And in parallel to this whole world of generation, the field of representation learning has been making enormous, truly foundational strides, especially in areas like image recognition.
Yeah.
These techniques are all about teaching models to really understand and capture the fundamental patterns, features, concepts within data. That makes them incredibly powerful for downstream tasks like, say, classifying objects or detecting them in complex scenes.
But here's one thing that struck me reading this paper. With all those amazing advances in representation learning, why haven't those techniques seamlessly jumped over to making generative models significantly better?
That's a great question.
The authors highlight this puzzle, suggesting that generative models, because they're so focused on those regression objectives like denising, often don't have explicit regularization applied to the internal representations they're learning as they go through that process.
Right, that's a big point they make. And as they mentioned, people have tried to bridge that gap. You had methods like REPA, or representation alignment. Yeah, they tried to leverage the power of existing representation learning models. They worked by aligning the generative model's internal representations with those from pre-trained external models, like powerful vision transformers trained on massive data sets.
Okay.
While pioneering and showing potential, as the paper points out, this approach added complexity and introduced significant external dependencies. You needed that big pre-trained model.
Which brings us to the core idea of this paper, dispersive loss. What's the intuition here? When I hear dispersive, I think about things spreading out. Is that the idea encouraging those internal representations, the model learns to disperse or spread out within the model's hidden space?
That's exactly it. Think of the analogy the paper uses, which I found helpful. It's kind of like the repulsion part of contrastive learning.
Okay.
Where you explicitly push dissimilar things away from each other in the representation space. But, and this is the crucial distinction, it doesn't need the attraction part. It doesn't require you to define or provide positive pairs, pairs of things that should be similar and pulled closer together.
Right.
The standard diffusion loss, that denoising objective we talked about earlier, already handles the necessary alignment or reconstruction needed to generate the image correctly. This dispersive loss just adds the pushing apart aspect.
And they make a big claim about this.
Yeah.
It's a plug-and-play regularizer. For you, the model developer who might want to try this out, what does that mean in practical terms? I mean, that sounds almost too good to be true for a cutting-edge research technique.
Well, yeah, it does sound good. And the paper really emphasizes its minimalist nature. And that's where the plug and play comes in. It means it's designed to be incredibly simple to just drop into an existing model architecture and training pipeline.
Yeah.
It requires no pre-training specific to this loss. You don't need any additional parameters added to your existing model. And crucially, it doesn't require any external data beyond the noisy images you're already using for training.
So it just uses the batch itself.
Exactly. It simply works by looking at the intermediate representations of the same batch of noisy images that the model is already processing for the standard diffusion loss. They state it introduces negligible overhead, which, for researchers and developers is a huge plus. Less complexity, less compute.
Okay, so we know the intuition push representations apart. How does the paper say they actually do that in the model? Diving a little into the technical side, I saw it's added as a second term, some lambda times the dispersive loss, LDisp, alongside the original diffusion loss, LDiff. And it's applied directly to those intermediate layers without needing any extra components like projection heads.
Right. That's the mechanical bit, yeah. And what's fascinating here is that dispersive loss isn't a single rigid formula. It's described as a class of objectives.
A class, okay.
The paper shows how you can derive variants of it from standard contrastive losses you might be familiar with, like info and C or hinge or covariance loss.
Right, info and C, I know that one.
Simply by dropping the positive pair component from their objectives, you just keep the part that pushes things apart.
I see. One interesting finding from their experiments jumped out at me. When they tried different variants of this dispersive loss, the info and C version using Ind2 distance performed best.
Yes, that was notable.
Now that Ind2 distance bit is interesting because it's different from what's common in traditional self-supervised learning, where cosine similarity is often preferred, usually after normalizing the representations.
Right, normalization is pretty standard there.
The paper notes they didn't normalize the representations before computing the U2 distance. They hypothesized this encourages more dispersion, not just in direction, but also in magnitude.
Pushing them further apart in the space overall.
They also highlighted the simplicity of its implementation, giving you the concept of algorithm 1, showing how straightforward it is to integrate. Just a few lines of code, it seems.
Exactly. Moving on to what the experiments actually showed. The paper evaluated dispersive loss extensively on standard and strong baseline transformer models like DiT and SiT.
The big ones.
On the large-scale ImageNet dataset. What was a consistent finding across these tests? It consistently improved performance, measured by metrics like FID, that's the freshet inception distance.
Lower is better for FID.
Right. Lower is better, yes. It's a standard score for assessing the quality and diversity of generated images. And dispersive loss consistently lowered the FID score.
They also had a key comparison in the paper between using their dispersive loss and trying to apply a traditional contrastive loss directly in this generative setting.
Ah, yes, that was important.
Why did they find that traditional contrastive loss struggled?
Well, the paper suggests it was very sensitive to the noise levels between the two views needed for contrastive learning. You need two versions of the input to contrast.
Right.
Aligning views with substantially different noise levels seemed to create interference and actually impaired learning. It confused the model, basically.
Okay, that makes sense.
Dispersive loss, by contrast, worked on a single view batch at any given noise level and didn't have this interference problem. So it led to better results, even compared to contrastive learning, where they carefully tuned the noise levels.
Interesting. So working on just one view avoids that whole issue.
Precisely. The paper also looked into where best to apply the loss within the model architecture. Which layers.
Yeah. So
they found that applying it even to a single intermediate block was effective and improved results.
Just one?
Just one block still gave a boost. And interestingly, applying it to just one block seemed to influence the representation norms in all the blocks throughout the network, not just the one it was applied to. They showed that in one of their figures.
Ah, like a ripple effect.
Kind of, yeah. But ultimately, applying it to all blocks where features are processed gave the best overall FID result. So spreading it throughout the network was optimal.
They also looked at performance across different model sizes, the small, base, large, and extra large variants of DiT and SiT models. And another interesting observation was that the stronger, larger baselines seemed to benefit more from the regularization effect of dispersive loss.
Yes, that supports their argument.
This really backs up their idea that this technique is primarily acting as a beneficial regularizer, especially for those larger, more capable models that have more capacity and might be more prone to issues like collapsing modes or overfitting to reconstruction.
Exactly. It helps keep those powerful models better behaved, you could say.
Okay. Now let's place dispersive loss in context, especially revisiting that comparison with REPA you mentioned earlier.
Right, REPA. The paper frames the key difference not just in terms of the mathematical objective, but the system-level implications. And this is a huge point.
System level, meaning?
Meaning the practicalities, the dependencies. Look at the massive external dependencies of REPA. It relied on a pre-trained DynoV2 model, which itself had, 1.1 billion parameters?
Whoa.
Was trained on 142 million images, requiring compute equivalent to 1,500 ImageNet epochs just for the pre-training of that external model.
That's a lot.
It's enormous. Contrast that with dispersive loss requiring none of that No external pre-training, no external data, no extra parameters added to your generative model.
Wow.
This is a significant point about efficiency, accessibility, and ease of implementation. It makes it much more practical for many researchers and developers to actually use.
That really puts the minimalist claim into perspective. And they went further to show the versatility of the technique, which I thought was really impressive.
Right.
It wasn't just for those multi-step diffusion models we've been discussing.
No, they pushed it further.
They successfully applied it to one-step generative models designed to generate an image in a single pass, which is much faster, right?
Much faster, yeah, a big goal in the field.
Specifically, they integrated it into the recent MeanFlow framework. The results showed it improved MeanFlow's performance significantly and even helped it achieve a new state-of-the-art result in one-step generation.
That's right.
Going from a 3.43 baseline FID down to 3.21. That's a noticeable jump for a single-step model.
It really is. It shows the technique isn't just cleaning things up in slow diffusion. It can actively improve these very fast models, too.
And they also demonstrated its application beyond transformer architectures.
Yes, they didn't stop there.
Applying it to a standard convolution-based UNet model on a different, smaller dataset, CFR10.
Right, showing it's not just some transformer trick.
This shows that the approach is not limited to just large transformer models or ImageNet, but has broader applicability across different architectures and data scales.
Definitely suggests a more general principle at play.
So, to wrap this deep dive up, the main takeaway here feels pretty clear. Dispersive loss offers a surprisingly simple, elegant, and effective way to add valuable regularization to generative models.
Right. As the paper highlights, its key benefits are that it's minimalist, it's plug and play, it's entirely self-contained, you just need your training batch, and it consistently improves performance across various settings.
Yeah.
Without interfering with the core generative process the model is already using, it just adds this helpful nudge.
And here's a thought to leave you with. One, the paper itself raises in its conclusion. Given how simple and effective this positive-free dispersive regularization approach is in pushing representations apart in hidden space, could this same principle be beneficial in other areas of deep learning? Areas like image recognition or other tasks where representation learning is absolutely central, even when you're trying to learn fine-grained similarity.
That's the big question, isn't it? It raises the interesting possibility of whether this kind of repulsion-only mechanism is a powerful general regularization strategy worth exploring far beyond just generative modeling. Could it help in classification, segmentation? Who knows?
Something to mull over as you next marvel at those amazing AI-generated images.
Definitely food for thought.